All right, y'all. Today we're going to be talking about limits graphically. So limits graphically is kind of the first way we're going to explore them today. But before we can get to that, we want to talk about what does a limit really mean. So when we look at a limit, we see this limit notation, and we read it as limit as x approaches c of f of x is equal to L, some value L. So just a couple of things. So this LIM does stand for limit. This x approaches c, that is how we read it, as x approaches c, with c being some constant value. Okay, then of course f of x is our function. And then L being some value of y. So we have the limit as x approaches c, which should be some constant of the function, and then that's equal to some value of y. That's how we read our limit notation. So let's look at some examples, okay? Because truly a limit is very similar to a function in that we're going to get an x value, and if we have an x value, we can plug it in, okay? So let's look at our very first example. We have the limit as x approaches 4 of 3x squared. So just like a function, I'm given an x value here, 4, and I want to know what the value of this limit would be as x approaches 4. So because I have a function, I have an x value I can plug into, I can just plug 4 in, so 3 times 4 squared, which would be equal to 3 times 16, which is equal to 48. Okay? Likewise, I can do the same thing for my next one. So I have the limit as x approaches 3 of x plus 3. So once again, I have a value of x and I have a function. So I can plug in my x value. So 3 plus 3 is equal to 6. So relatively straightforward so far, but we're going to see something a little bit different pop up on our next one, and this is what's going to really separate our limits from our functions. We have the limit as x approaches 3 of x squared minus 9 over x minus 3. So once again, we have a function and we have a value of x, so we're going to plug it in. So 3 squared minus 9 over 3 minus 3 is equal to 9 minus 9 over 0, which is equal to 0 over 0. Now, we've talked about this before, okay? We can't have this 0 over 0. We actually call it an indeterminate answer. And in our last unit in rationals, we talked about how that indeterminate means that the function is undefined there. Something is going on, maybe an asymptote, maybe in whole, that is making our function undefined at that value of 3, okay? But while with our function, we would stop and we would say our function is undefined, with our limit, we can actually find what that value of the function would equal at 3. And so we can do that by going back and seeing if we can factor or simplify anything. So x squared minus 9 can factor into x plus 3 times x minus 3. And then on the bottom, we still have our x minus 3, which of course now my x minus 3 and x minus 3 cancel out. So I get a new simplified limit of the limit as x approaches 3 of just x plus 3, which once again, now I can plug in my x value. So I would get 3 plus 3, which is equal to 6. So while originally, if this was just a function, I would have had to stop and say, well, the function is undefined there because of what we discovered, a whole there at an x value of 3. In this one, we get to go a little bit further and actually simplify and say, well, with the limit, I can say the value of the limit is 6, which means even though there is a hole at 3, the function is going to look like it gets to that y value of 6. And we're going to explore this a little bit more graphically. It starts to make a little bit more sense. So let's look at our first graph. So we have f of 3, and we have the limit as x approaches 3 of f of x. So for f of 3, I'm going to go to my graph, and I'm going to find my x value of 3. And I'm going to see my function has a point there, so I'm going to find the y value, which is 2. And that is what my function is equal to at 3. So I go to the x value of 3, and I pull out the y value of 2. For our limit, remember that we read a limit as x approaches some constant value. So this really is kind of seen in the graphical representation, and that we approach that x value from the left, and we approach that x value from the right. Because any number, so like 3 on a number line, I can go towards 3 from numbers less than 3, and I can go towards 3 from numbers greater than 3. So we explain this by saying approaching from the left and approaching from the right. And as I approach my limit from both the left and the right, what y value does my function look like it gets to? Well, it looks like it gets to 2. So in this case, both my function value and my limit value are exactly the same. And you might notice that this is a continuous function. It doesn't have any breaks, holes, asymptotes, anything like that. So a lot of times with our continuous functions, our function value and our limit value should be the same. Okay, let's look at another graph that's maybe going to start to show the separation between a function and a limit. Okay, so this one's very similar, except now for its point, it has a hole instead of an actual colored in point. So for our function value, I'm going to go to x is equal to 5. I'm going to go up to my function. And unfortunately, there is a hole, which when there's a hole, what does that mean about my function value? It means my function is undefined. Okay, but for my limit I can approach from the left and the right. So as I go from the left and as I go from the right, while yes, there's still a hole there, my function looks like it gets to a y value of 1. So that's where my limit gets to kind of ignore our normal rules that our functions have to follow. The functions have to tell me what's happening right at the x value. The limit can tell me what does it look like should be happening, even if something different is happening right at that x value. And let's look at another situation. So I have this function here where it's got a hole, but then it actually has a point in the exact same spot. So for our function value, we have f of 5, so I'm going to an x value of 5. I'm going to go up. I find my point right here. It's at a y value of 1, so my function value would be 1. For my limit, once again, I approach my x value of 5 from both the left and the right. As I approach from the left and the right, my function looks like it gets to a y value of 3. So this would be a case where both the function and the limit exist, but they're a little bit different because where the function looks like it gets to is one y value, even though the limit or the point is somewhere else. Okay, so let's look at our last situation. This is probably our most eye-opening one. So we have our function, we have our limit, we have two different functions. This is definitely a piecewise situation where one has the point, one does not. So finding our f of 3 first, we go here to 3. We find that point. It's at a y value of 4. So f of 3 is equal to 4. Then for our limit, just like before, we have to approach our limit from the left and our limit from the right. But this time, the limit doesn't actually look like it gets to the same value. So unfortunately, because of this, I actually can't find my overall limit. But I can split my overall limit into two separate limits. So I can split this out into the limit as x approaches 3, the limit as x approaches 3 from the left, which I denote with a little negative exponent of f of x, and then the limit as x approaches 3 from the right, which I denote with that little plus sign exponent. And once again, of f of x. So my limit from the left looks like I get to a y value of 2. My limit from the right looks like I get to a y value of 4. And because this overall limit has to consider the left and the right side, if my left and my right side do not equal each other, we say that the overall limit does not exist, or D and E for short. Okay. So this is kind of really the key thing with limits is while they do get to cheat, they do still have some rules, and it's that the left and the right side have to be equal to the same thing for my overall limit to exist. So let's add some language to some of the things we discovered. So when you are not approaching the same y value from both sides, then the limit does not exist. When you are approaching the same y value from both sides, then the limit exists. However, we can approach the limit individually from either side, and we call this a one-sided limit. Hey, so I want you to go ahead and practice real quick by doing number 1 and number 2. And for number 1 and number 2, I want you to find the value of the function. I want you to find the limit as x approaches 1 of the function. And then I also want you to find the one-sided limit. So the limit as x approaches 1 from the left and the limit as x approaches 1 from the right. So go ahead and pause the video now and try these on your own, and then I'll explain them here in a second. All right, y'all. So hopefully you tried number 1 and number 2. Remember, we were finding the function value, the overall limit, and the left side and right-sided limit. So on number 1, we have a function value at 4. Our left side limit approaches and reaches a value of 1, while our right side limit approaches and reaches a value of 4. Those are not equal to each other, so we say the overall limit does not exist. And then on number 2, once again, we find our actual function value. So we go to our x value of 1, we get out a y value of 1. Our overall limit, we have to do the left side and the right side. The left side is going all the way down to -5, while the right side is going all the way up to +7. -5 and +7 are not equal to each other. So once again, our overall limit is D and E. All right, y'all. I hope that answers all your questions about limits. If you have any more, please feel free to come to tutorials or ask me during class. But go ahead and try that first page of the homework. Thank you.